All right, question 91 is our next key concept. It's key concept number 8, and it says, for things at the same temperature, the thing with more molecules has more total kinetic energy, or thermal energy, than the thing with fewer molecules. So basically, if you have something like two things that are both at 90 degrees, the larger one has more energy, the smaller one has less energy. Even though they're the same temperature, the bigger one will take a lot longer to cool down. So pause this, copy it down. All right, so you just read about what thermal energy is and how it is different from temperature and why it depends in part on the number of molecules that make up a thing. Knowing all of this is going to help us as we start to investigate why things change temperature a lot or just a little. So, I want you to think about this. Which would you prefer? Would you rather spend 10 hours in a bathtub filled with water that starts out at 120 degrees? Or would you rather spend 10 hours in a swimming pool filled with water that starts out at 110 degrees? Choose wisely, because one of these options you will survive and the other you will not. Okay, so the idea here is that the bathtub filled with water, even though the bathtub is warmer at 120 degrees, it is so much smaller that it will cool down when you get in. You won't spend like 10 hours at 120 degrees. It's going to cool down to 100 degrees, 90 degrees, 80 degrees within the first hour or two. The 10 hours in a swimming pool, the swimming pool will take days to cool down from this temperature, and this is warm enough to kill you. So because the swimming pool is so much larger, it has more kinetic energy in total, even though it has a lower temperature. So it would take a lot longer for this swimming pool to cool down, and it would overheat you and kill you. So, we are going to do an activity called an energy cube model to help us investigate our question, which is what determines how much something will change temperature by. We're going to use their energy cube model to represent molecules and energy. This will help us visualize and think about how different systems reach equilibrium. We're going to use these models to show energy transfer. So first of all, we've got this page with 3 different trials, and in each trial we have object A and object B and the amount of kinetic energy they have in A and B. So I'm going to switch over to my overhead camera. For trial 1, I have object A, which has 6 molecules in it, so this is the larger object, and we've got object B, which only has 2 molecules in it. It is the smaller object. And our goal is to replicate this page each time. So for this one, object A, the average kinetic energy is how many energy cubes we put on each circle or each molecule. So for object A, the average is 4 for trial 1, so 4, 4, 4, 4, 4, and 4. And object B has an average of 4, so we have 4 and 4. So the question is, first of all, what is the total kinetic energy? Right there, you're going to calculate that. So the total kinetic energy of A, 4 plus 4 plus 4 plus 4 plus 4 plus 4. 4 times 6 is 24. So you're at 24 in there. The total energy for object B, 4, 8. You put 8 right here. And wait for a moment for the announcements to stop. Okay, so right now these two objects are separated. What happens when we bring them together to touch? When two objects touch, their molecules start colliding and they start transferring energy. The way they transfer energy is they transfer from the hotter object into the colder object. Right now, the temperature of this one is 4 and the temperature of this one is 4. So we don't expect any energy to transfer. So over here on the right side, maybe it'd be better if I jump over to the presentation. Over here on the right side, which box are we going to select? We're going to say that the system is at equilibrium because the objects are the same temperature. So this top box is what you're going to check off. There shouldn't be any energy transfer back and forth between the two objects because they are all already at the same temperature. So I'm going to move all of this to the side, and we're going to look at trial 2. let's see, trial 2, object A has 3 kilojoules of energy on each molecule. So here, let's go over and look at it. Object A is supposed to start with 3 on each molecule, and object B is supposed to start with 7 on each molecule. So let's check this. Double check it. 1, 2, 3, 4, 5, 6, 7. 2, 4, 6, 7. Okay, so object A and object B are set up. So on our sheet where we're supposed to figure out the total kinetic energy, object A, there are 6 molecules, 3 kilojoules each. 6 times 3 is 18. There's 18 joules of kinetic energy for object A for the total. Object B, there's only 2 molecules, and they each have 7. So what's the total? 2 times 7 is 14. So that's for our total kinetic energy. Now, when we bring these molecules together and they touch, what is going to happen? This one's hotter, this one's cooler. So we're going to have energy transfer from the hotter one into the cooler one until they're at equilibrium, which is when they're at the same temperature. So let's go ahead and show that. They collide, they start transferring energy. Energy moves over until all of them are the same. So here I'm just moving 1 cube from each molecule over. So here we have 4, 4, 4, 4, 4, 4, 4, 4. All the molecules are the same temperature because they all have the same average. That means that they have now reached equilibrium. So before we moved it, it said, what is the state of the system? Choose from one option below. Before when we started, the system was not at equilibrium because object A is colder than object B. Object B started with 7, so it was the hotter one. A was the cooler one. It was not at equilibrium. Energy was going to flow. Let's look at the setup for the third one. Trial 3. Okay, so in trial 3, it says that A starts with 5 kilojoules, B starts with 1. So each molecule in A has 5 things of energy, each molecule in B has 1. So when these are separated, is this at equilibrium? The answer to this is no, because object A is much warmer and has a much higher average. Object B has a much lower average. So when these come in contact, it's going to start moving energy. We're just going to move energy one at a time to each molecule. And now we end with all molecules having 4. So B increased by quite a bit as it gained energy from object A. Object A was warmer, object B was cooler. Because object A was so large, we had to move a lot more molecules over here to get to equilibrium than we did in trial 2. In trial 2, we just moved molecules over here, and A only increased by 1 degree because A is much larger, so it took more energy moving over to increase each one of these. When we did the reverse, when we moved energy from A over to B, B is much smaller, so it was a lot easier to heat up. We increased our temperature by 3. There was 1 in here before, and we had to move 3 over. So this got a lot hotter because it's a lot smaller, and it's easier to heat up smaller objects. So here in our energy cube model, before we transferred anything over, we're going to say that the system was not at equilibrium because object B was colder than object A. B was colder than A, so the system was not at equilibrium there.